to a logic level 0. You let things float and you're liable to blow gates and do all sorts of strange things. So try never to let a control line just float. So floating it's not an option. What do I want to do? I want to control it. When do I want this bottom chunk of memory to be active? When A2 is 1.
Mm-hmm.
But what do I need here to make it this chip active? This line has to do what?
It has to be low.
Has to be low. Well, how do I make a 1 into a 0?
With a NOT gate.
So, will this work? What happens when A2 is 0? This guy is selected or not selected, the one on top?
When A2 is 0, it's selected.
What about this one down here? It's not selected.
Not
Put a
selected.
0 in here, what do you get out?
A 1.
So it's not selected. What happens when we go to our top half of memory and A2 is a 1? This guy is what? It's not selected, right? So its outputs are in their tri-stated region and just open circuited. They have no connection to the bus. Here, though, this guy is going to, because we put a 1 here, we'll get a 0 here. All the outputs here are going to come out of the tri-state, and it'll either be a 0 or a 1. Understand what's going on? I mean, this is really a simple concept. Everybody okay? Yeah? Okay. So what would I do if I wanted to make a 16 by 9 memory?
You would need 12 cells.
Want to vote for 12? Are we okay with 12? Yeah, we would. Okay.
Good. I can do
So let's put these guys up. Okay, if I wanted a 4 by 9, I would just do this, right? Again, how many address lines are going to go to each one of those? 2.
2.
Right? A0, A1. And it goes all the way through, right? Well, you said we're going to need 12 of these guys. How many address lines am I going to need to uniquely specify one of 16 words?
4.
4 of them. So we're going to have an A3, an A2, an A1, and an A0. A1 and A0 are going to go to what?
It should be the same.
Last memory
It should be the
chip
same.
that we got. So all of these guys will see A1, A0, A1, A0, A1, A0. The data lines, well, see, that starts getting confusing. So let's do this. I'm going to bring one line down, call it 3. So I've got my 9 I/O lines there. Well, how am I going to select the bank? Which one of these, which will you consider to be the bottom of the memory? And which one the top? And it's immaterial which one you choose. What do I want this one to be? Top of memory or bottom of memory? Somebody? Top. Okay. So if it's the top of memory, what will its A3, A2 be?
0, 0.
Not if it's a top.
Because that's on the bottom. 1, 1.
Okay. It would be 1, 1. And so this guy down here, this row ought to be what? The bottom of the memory? And so what do we want its A3, A2 lines to be?
That would be
0, 0. And this would be 0, 1, 1, 0. Okay? So now, how are we going to make this happen? I'm going to have all these chip select lines. Do I have, yeah, it's active low. How am I going to generate that chip select bar line for that? What is it I'm trying to recognize? Having a what?
A 1,
1, 1, right? How will I come up with something that will tell me if I have a 1, 1 there? An AND gate, correct? Okay. So here's an AND gate. This is going to be A2, A3. If both of those are 1, what's my output?
1.
1. But what is it that I want to control this guy?
Low.
Active low.
So you.
Do you see if I put a NAND gate there? That top row of memories will be accessed. Everybody okay? Okay, now comes the big question. What do I do with the rest of them? What about this chip select here? What do I have to do in order to say, hey, I want the bottom chunk of memory?
A3 and A2 must be 0.
Everybody okay with that? A3 and A2 have to be what?
0.
0. And I have to recognize that. So I'm going to take and invert those guys. So here's A3, A2. Invert them and then do what with them?
Then put an AND gate.
Then AND them, right? But I want this guy to be active what?
Low.
Low.
So you NAND.
So we'll do a NOT gate. So again, the whole reason we went through combinational logic was not to do insurance problems, it's to help us out here with our digital circuits. Yes, no, everybody all right? We're going to be kind of fortunate in that we're dealing with microcontrollers. Okay? What was our definition of a microcontroller?
You can interface it with the outside world and change what's on it.
Okay, we can interface it to the outside world, that's all good. Still not the exact good definition we want. It is a single chip computer. That means it has what? It has memory, I/O stuff,
Address.
processing unit. Okay. So all of our memory in that we're going to have inside the chip. What happens if we don't have enough memory for data or don't have enough memory for program?
Things
We'll
get
go buy a different chip. Okay. So in your computer, on your desktop or your laptop, it's got this CPU, central processing unit, and then all this memory and other stuff is added external to that with different chips. And then you have to be really, really concerned about how to do this type of stuff here. So your CPU is going to have address lines and data lines to go out and interface with these other chips. Oh, questions? No? Good, okay. So this is as far as we're going to go for the exam. We're going to start on Friday then is to do number systems. Okay, so let's talk about number systems here. The homework I gave you, I think I told you, I can't remember what it was, you're going to be building up some larger memory with smaller cells. If your basic cell was 512 by 8, if you're so how many I/O lines will it have?
9.
Eight. Address lines?
9.
Yes, 9 address lines. If you wanted to make a 1024 by 16 memory, how many of these chips would you need? Need 4. Correct? Okay. So let's take a look at positive integer numbers right now. If I had a this type of memory, 512 by 8, what is the largest integer I could represent? Pardon?
9 nines.
I found it up.
I'm going to give you a hint. It's a power of 2.
Read that.
Wasn't much of a hint.
No. Is it 8 because there's only 8 bits? No, not 8. 256 because there's only 8 bits.
Still not right. Close. I did not ask how many integers I could represent. I asked what is the largest. Reaching.
I'm using every single bit on it.
And then some. I like the -1 business.
255?
255. What's 512? What is that? What does that number represent?
2 to the 9.
Yes, that's true. It is the number of chunks or words of memory in this cell.
Mm-hmm.
Each word is how big?
8 bits.
8 bits. In 8 bits, how many unique things can you represent?
256.
256 unique things. 0 is a unique thing. So if we start counting 0, 1, 2, the most we can go up to is 255. Correct?
Mm-hmm.
If I had a 10-bit word, let's do this. Got a 10-bit A to D converter. A to D stands for
Analog to digital.
analog to digital. How many unique things can I represent?
To the 10th, 1020.
1024.
1,024 unique things.
Mm-hmm.
Okay, one of the things I haven't talked about, but if I said I had a 1K bit memory, how many bits are in that memory?
1,000.
It's a trick question. Okay. One large K is 2 to the 10.
It's 2 to the 10.
It's 1024. Okay, so if you're talking about number of bytes in your memory, if it's kilobits, kilobytes, or whatever, it's always 1024. Okay, it's not 1,000. But large K versus small K. Okay. All right, we will stop there for today.